Hey everyone, I have got super exciting news to share with you today. Welcome back to Code and Codes. I'm thrilled because the AI world just got a major upgrade. Llama 3.2 has arrived and it is game changer. Imagine compressing a model from 8 billion parameters to just 1 billion and the results are incredible. So in this video, I will share all the exciting details including what is new in Llama 3.2, how it was compressed so dramatically, a hands-on comparison of Llama 3.1 versus Llama 3.2 variants, and the programmatic experiments to help you decide which one is the best. So trust me, you don't want to miss this. Hit the subscribe button and stay tuned for the future of AI right here. So let's jump in. So before starting to the actual thing, first I want to show you the web page where officially they released this news about Llama 3.2 revolutionizing edge AI and vision with open customizable models. So in this website they given all the information about this model, and they shown the high level approach like how they prune this model and all the benchmark, and some demos are also be there. So from this website I summarized the content and I researched some of the other things, and whatever the important information is there that I extracted so you can understand this Llama 3.2 into the better and the simpler version. So let's start. Okay, yeah, so let's start this thing. Okay, yeah, so I will start with the release of Llama 3.2. So what and all the key features are there? So the Llama 3.2 actually they released for the two main variants. One is for the vision LLM and one is for the text only models. So inside the vision LLM they released the small and the medium sized vision LLM which having the parameter size 11 billion and the 90 billion respective. And they also released inside the text only model, which is the lightweight model, which having the parameter size 1 billion and the 3 billion. So this vision LLM like we can able to use for the image as well as the text, and the text only models which we can able to fit into the edge and mobile devices, and including the pre-trained and the instruction tune version, so that all the versions actually they released. So let's start with the model specification, which is the text only model. So as I said, there is the 1 billion and the 3 billion models designed for edge and the mobile devices, and it having the support of the context length 128k tokens. So it is similar to the Llama 3.1 8 billion, which also having the context length of the 128k tokens, but as compared to the Llama 3, it having only the 8k tokens, so it is the better than that. So the third point is like optimized for on-device task, so we can able to leverage this model for the summarization, instruction following and rewriting. Also they mentioned like they taken the partnership with the Qualcomm and the MediaTek hardware, and they optimized the model for the ARM processor, and they enable the model specifically for this Qualcomm and MediaTek, so we can enable this model on such edge platform. And also the models offer the improved multilingual support for 8 languages including English, German, French, Italian, Portuguese, Hindi, Spanish and Thai. So with specific to the 3 billion model, so what and all other variants of model which they are outperforming. So with respect to the 3 billion model, so this model is outperform Gamma 2.26 billion and 3.5 mini models on the task such as the following: instruction, summarization, prompt rewriting and the tool use. And 1 billion parameter model, which is the Llama 3.2 1 billion parameter model, so it is competitive with other 1 to 3 billion parameter models, and its use cases include the personal information management, multi-language knowledge retrieval and the rewriting task running locally on the edge. Okay, so the next is with respect to the vision LLM model specification. So the Llama 3.2 1 billion and the 90 billion vision models are drop in the replacement for their corresponding text model equivalents. So this they given the statement like we can able these models are like the replacement for their corresponding text model equivalents, and it is exceeding on the image understanding task compared to the closed model such as the Cloudy 3. So this model having the broad ecosystem support and models available for the fine tuning using the torch run, development through the torch chart for the custom application that is also be there, and the pre-trained and aligned models available for the users. And also user can try models using the Meta AI's smart assistant. So this thing I will tell you into the next slide. So they having kind of agentic use cases. So on that Meta AI smart assistant use case, like we can able to use this model. So next they having the update about the Llama Stack. So Llama Stack is kind of end-to-end stack which is like it is implemented for all the end users, where with the help of means there are the end-to-end APIs are there, and with the help of that on the no code environment they can able to use that API, and they can able to leverage for the purpose they having. Okay, so this stack actually it is implemented in such layer. So on the bottom there is the hardware will be there, which is having the GPU, accelerator, and storage. On the top of that there are the two layers are there. One is the data layer and one is the models. So inside the data layers, whatever the pre-training, preference, and the post-training data is there, that will be there. And inside the models, the core, safety, and customized models are there. So on the top of that we having this model toolchain APIs, and in that for the model development and production tools are there. For example, for the batch inference, real-time inference, quantized inference, continual pre-training, for the evaluation, whatever the publicly available data sets are there for that, then the fine-tuning, pre-training, reward scoring, and synthetic data generation. So for that they are giving the APIs, and on the top of that we can able to see this agentic system APIs, where the system component orchestration will be there. For example, this prompt store, so this is kind of the prompt library where the different prompts we can able to see. Then the assistant will be there, shields are there, the memory and the orchestra component is there, and on the top of that the whatever end user is there, it can able to leverage the agentic apps, which is the end applications. So the key developments into that, the API implementation. So they successfully built a reference implementation of the APIs for the inference, tool edge, and the retrieval augmented generation, which is nothing but RAG. So they're having the partnership collaboration, like they are collaborating with the partners to adapt their system as API providers. They provides a unified endpoint for the developers. And also inside the community impact, so they are delivering a simplified and consistent experience for the developers, and the support for the multiple environments is already available. So you can leverage this Llama Stack on the on-prem, cloud, single node, or on device. So next is where actually we can able to see this Llama 3.2. So for the release of Llama 3.2, so availability and download. So we can able to access this Llama 3.2 directly from we can download the models from the llama.com, and also the Hugging Face is providing the complete series of the model which is the Llama for the Llama 3.2. And also it having the immediate development options on the partner platforms like the AMD, AWS, Databricks, Dell, Google Cloud, IBM, Intel, Microsoft Azure, NVIDIA, Oracle Cloud, Snowflake. So there actually we can start the immediate development. Okay, so on the Hugging Face, if I show you, so so if you search on the Hugging Face this Llama 3.2 directory, so it will looks like this. So here all the versions of this Llama 3.2, including the 1 billion, 3 billion, 1 billion Instruct, 3 billion Instruct. Okay, so this guard version, the int4 version, then the 11 billion vision, 11 billion vision Instruct, 90 billion vision Instruct. Okay, and the guard version of that. So all the versions of this actually we can able to see on the Hugging Face, and also from the Llama side also you can able to download these models. Okay. Okay, so the next thing is, yeah, so now like we will see how these models actually they pruned, like they compressed from the 8 billion to the this 1 billion thing or the 3 billion thing. Okay, so it is regarding these text only models. So on the site actually they given the high level details. So first we will go through that, then we will see some of the technical aspect of this, like how actually they prune this model. So first I will start from there. Okay. Okay, so for the, yeah, so for the pruning and the distillation, so this is also one technique is there. So first actually they are applying this pruning thing. So I will make this thing. So first let's try to understand this diagram, like how actually they are doing this compression of the model, like applying the pruning, and on the top of that they are applying the distillation. So first let's understand what is the pruning. So pruning is the technique where we can able to remove whatever the less important parameters or the less important component or the redundant layers, okay, from the model architecture by using some kind of the techniques. So there are the two techniques are there for that. One is the structured pruning and one is the unstructured pruning. So inside the structured pruning, like whatever the complete component or complete neuron or complete filter, okay, or complete layer or attention head or embedding channel, so such kind of the complete component it can be able to remove from the structured pruning. And from the unstructured pruning, like instead of removing that complete component, so it will try to means whatever the less importance individual weights are there, it will try to remove that, okay, means making them as it is as to the zero. So for the Llama 3.2 actually how which technique they use, so they use the called the structure training. So after this diagram explanation I will show you how actually they are doing that. Okay, so so let's understand this diagram. So here you can able to see this is the inference stack, and inside the inference stack we can able to see there are three models are there. One is the Llama 3.1 8 billion pre-trained, then the Llama 3.1 70 billion pre-trained, and then we having this one Llama 3.1 405 billion instruct. Okay, so the first step is like they having the pre-training data for these both models. Okay, so the same data actually it is there. So from that what they are doing, they are taking some portion of that data, and whatever this mixed data it is there which is used for the Llama 3.8 billion pre-trained and Llama 3.1 70 billion pre-trained. So that mixed data first they are passing to this both model in order to create the logic data. So what is actually this logic data? So logic data is like it means if you see the Llama 3. Means Llama architecture, it is the decoder only architecture. So inside that before applying the softmax function, so whatever the output it is there, so that is called as the logits. So before the softmax layers there is the one linear layer will be there, and on that whatever the output actually it is producing, so that raw output actually they are taking which is called as the logits. So logic data is nothing but the data which is without applied this softmax function. Okay, means without getting the probabilities of that particular raw thing. So that actually they are taking where, and this when we can where we can able to find this data, whatever the before softmax layer, whatever the linear layer is there, on that we can able to find this data. So like that mixed data they are passing to these both 3.18 billion pretend and 70 billion pretend, and they are taking this logic data. Okay, so this logic data actually they are using for the distillation, so that I will tell you how actually they are using. But before that they are applying this structured pruning. So inside the structured pruning what they are doing, like means whatever the components are there. Okay, so this component, it can be anything. So it is some specific layers, or it is the some attention heads, okay, or it is the neurons inside the feed forward network, or it is the embedding channel. Okay, so they are removing such kind of the less important component in the structured way, means into the systematic approach. So how actually they are doing that also I will show, but just keep in your mind, like they are doing this pruning, and inside this structured pruning they will get this Llama 3.2 1 billion or the 3 billion pre-trained model. Okay, then on the top of that, means once you prune the model in that way, so in order to overcome whatever the accuracy means accuracy which we are getting the less accuracy, in order to overcome that thing, they are applying the training called as the distillation. So distillation is the training in which there is the one bigger model is there, which is called as the teacher model. So in this case, that teacher model they are using as the Llama 3.1 billion pre-trained, and one is the student model will be there. So whatever the pruned version of this Llama 3.1 billion that they are using as the student model, and this both model actually it will be trained on this logic data. Okay, so this same data set they will pass to this pruned version of that, and whatever the linear layer of that pruned version, from there they will get this raw outputs which is called as the logic data. Then that logics from the pruned model and the logics from this teacher model, they will compare. Okay, they will like take the cosine similarity or other matrices actually they will take, and with respect to that actually they will apply that losses and also what and all the losses actually they are using inside the distillation, that I will tell you. But in this way actually they will train the model with the distillation approach. Okay, so once this model gets trained with the distillation, then what they are doing, okay, in the inference stack they having already this Llama 3.1 405 billion instruct. So to this model they are passing the synthetic data prompts which can able to generate the synthetic data. Then this synthetic data plus they already having this collected fine-tuning data, so this both data they are again they are doing the instruction fine-tuning on that in order to get the final Llama 3.1 billion or the 3 billion instruct model. So this is like overall the process is there, like how they are doing this pruning plus distillation and getting the final Llama 3.2 1 billion or the 3 billion instruct model. Okay, so now let's understand the more about this pruning thing. Okay. Okay, so let me open. Okay, so yeah, so let me select my pen. Okay, so as I said they are using this structured pruning. Okay, so this structured pruning it can be applied to the all the components of our architecture. Okay, it can be the neurons into the feed forward network, or it can be the entire layers. Okay, it can be entire block, or it can be the attention heads. Okay, so there are the actually the two types of pruning structural pruning is there. One it is called the one pruning it is called as depth pruning. Okay, so inside the depth pruning it is what actually they are doing, what will be happen. Okay, so inside the depth pruning, so like inside the depth pruning actually whatever the layers are there, so that actually they try to remove whatever the layer which is the less impactable or which having the less importance in order to generate the final output. So such layers actually they are trying to remove. So depth pruning it is applied for the layers, and there are the another pruning structure pruning it is there which is called as the width pruning. Okay, so inside the width pruning what they will do, so whatever the internal components are there, for example this kind of the attention heads. Okay, attention heads are there. Okay, or uh, the embedding channels will be there. Okay, or whatever this feed forward network neurons are there. Okay, so this kind of or also this attention head, so that already I covered. So this kind of the internal components, they are pruning inside the width pruning. Okay, so in the Llama 3.2 actually they used this both thing. Okay, so what actually they did, so so first, okay, so how actually they did. Okay, so suppose this is one kind of one architecture. Suppose you take as the consider like this is the decoder only board block which we having. Okay, so after collecting the logic data, okay, so where is the logic data actually we can able to get. So before softmax layer, whatever the linear layer will be there, so from that whatever the output which we are getting, so this output it is called as the logits. Okay, so first they are pre-computing these logits with respect to that mixed data. Okay, and then they are actually finding out like which part of the model is the less important or the less significant. So it is either it is neurons or the attention heads or the layers or the embedding channels, it can be anything. So in order to find out what actually they are doing, they are finding out the various matrices. It can be used for that in order to determine the importance. So the matrices is like finding out the magnitude of the weights. So weights with the smaller magnitude contribute the less to the model prediction. So how actually they are finding out this magnitude? So there is the most common method is to finding out the magnitude of weights. It is applying the L2 norm of the L2 norm on the weights. Okay, like L2 norm actually how actually we can able to find out. So L2 norm, it is like the square root of summation of I is equal to 1 to m, okay, w square. Okay, so this is called as the L2 norm. Okay, so then other method is there are also there, which is finding out the L1 norm of the weights, but the most common and effective method is to find out the magnitude of the weights. It is called as the L2 norm. Then also they are doing the sensitivity analysis, like assess how much the model's output changes when the specific weights are the altered or zeroed out. Okay, so that also they can use. Okay, then the logit score. Okay, so they will analyze like after removing each of the components. For example, if I remove some of the neurons, or if I remove some of the attention heads, or even if I remove some of the layers or the embedding channels, then how this logit scores will be generated. Okay, so according to that they will rank all these components with respect to that, and they will whatever the means 30% or 40% of whatever the less important components are there, they will directly remove. Okay, so these three things are there, like they are applying into that. Okay, so how actually they are doing. Okay, so in one of the blog actually I saw the explanation very well, so I will tell you like how they are doing. Okay, so there are the total 5 steps are there in order to prune plus distillation. Okay, so first thing, whatever your large model it is there, so whatever the trend LLM is there, they are taking. Okay, then they are estimating the importance. Okay, so how they are estimating the importance. So like as I said, whatever this third method it is there. Okay, like logit score. So on the depends on that, they are finding out the each component importance, like how much importance of each of the layer or each of the attention head or each of the feed forward network or the embedded channel. So according to that, they are estimating the importance. Like they will remove some such kind of the component, and they will check like how the logits score is changing by taking the reference of the logits score of the actual model. So according to that, they are ranking all these components, okay, from the higher rank to the lower rank. Then after that, they are applying the trimming. Okay, means whatever the less ranked things are there, components are there, or which having the less important into the overall architecture, they are removing such a thing. Okay, for example, from the embedding layer, suppose embedding 1 and embedding 3 is less important, so into the next step they will directly trim this. Okay, so now we will get the final trimmed version of the model, so which we can call as the pruned model. So this pruned model, it is not that much accurate, so again on the top of that they are applying this distillation. Okay, so after applying this distillation, like we will get the output as close to the whatever the original model it is there. Okay, so like that, means in the two step actually it can able to do this. Okay, one is like means repeat these steps. Okay, means first we will do the repetition of this 5 step in order to convert the model from the 8 billion to the 3 billion. Okay, so once we get this 3 billion model, then again the same step we will apply in order to make this model from the 3 billion and the 1 billion. Okay, so in the two step actually it can able to do this thing, and also it is possible to make the pruning plus distillation from the directly from the 8 billion to the 1 billion. Okay, but they didn't disclose like either they did into the two step or into the one step. Okay, so this means in this way actually they pruned their model. Okay, so now let's check the next thing, like how they applied the distillation. So as I said, inside the distillation we having the two version. One is the teacher model. So this teacher model they are using this Llama 3.1 8 billion Instruct model, which is the large parameter model which having the parameters 8 billion parameters it having. Then one version it is called as the student model, which is it is either this model is Llama 3.2 1 billion or the Llama 3.2 3 billion model. Okay, so then whatever the pre-trained mixed data it is there on the top of means by feeding that data they are actually getting the logits. Okay, so logits like whatever the before the softmax layer, whatever the linear layer providing producing the output, they are keeping that output as the logits. Okay, so the same data set, the mixed data set, they are passing to the teacher model, and the same mixed data set they are passing to the student model. Okay, then this kind of the losses actually they are computing in order to train this model, in order to distillate this model. So first loss is embedding output loss. So for whatever the embedding layers are there, so from that whatever the loss actually it is there, they are computing. Then the next loss it is called as the MLP input loss. So this means this multi-head attentions means whatever output they are producing, it is the input to the feed forward network. So this feed forward network it is nothing but the MLP. So the MLP is the multi-layer perceptron. So this MLP input loss they are computing, which is the output of the multi-head attention. Then after that they are computing the encoder block output loss. So from this block, from this entire block, okay, whatever the output they are getting, so that ANC block output loss they are actually computing. Then the next loss is the LM head loss. So the LM is the language model head loss. So it is nothing but that linear layer only. So, okay, where we are getting the final logits. So that language model head loss they are computing, and the final loss is the logit loss. Okay, so means whatever the final logits which is producing this LM head, so on the top of that they are applying this logit loss. Okay, so here like the objective is like whatever this all the losses means whatever the losses between this teacher and the student model is there, the objective is like it's needs to be minimized that loss. Okay, so once this all the losses gets minimized, then we will get the model which is called as this distillated model, and it will produce the output which is close to the teacher model. Okay, which is nothing but Llama 3.1 8 billion. Okay, so in that way they are actually doing this distillation. Okay, So now like what we will do. So on the site actually they are if you can see, they are giving very good demos also. Okay, so that we will also see. Okay, so before that we will see like what and all the model evaluations actually they are did. So on the site you can able to access this thing where for the vision model and for this lightweight instruction tuned benchmarks actually they given. So for the vision instruction tuned benchmark, okay, so they use the benchmark like this MMMU Pro standard, okay, MMMU Pro vision math vista and all. And where they given this all these matrices like we can able to see the benchmarks like how these models are performing. So this vision model actually it is used for the image as well as the text. So for the text also they given the benchmarks, okay, like in order to consider this maths GPQA and MGSM and all. Then after that for the lightweight instruction tuned benchmark are also be there, where it is comparing this benchmark with the Llama 2 billion and 3.5 mini IT. Okay, so here you can able to see the different benchmarks which is already be there. Okay, so this kind of the evaluation thing actually they given. And also if you can able to see they given the demo, okay, like how this image understanding demo is there. So that also they given. So here actually you need to upload the image and it will create that brief description of that. So it is kind of very impressive demo also they given. Okay, and for the for this lightweight model demo, so for that the one of the demo is there for the mobile writing assistant demo. So here like on the runtime only it can able to assist you, like if you are typing something then you can this model can able to assist you like what the content actually we need to write. Okay, so this is like kind of very good demos actually they given on the site. So on the site you can able to access these demos as well. Okay, so now let's move to the our next topic. Okay, so okay, yeah, so yeah, so now like we will compare like programmatically by experiment like which model is producing like the good outputs. Okay, so for now we will compare this Llama 3.1 8 billion instruct with the Llama 3.2 1 billion instruct and Llama 3.1 3 billion instruct with respect to some of the aspect like what the minimum GPU memory actually be required, what is the inference time, the content length, like how much the good content this model can able to generate, okay, their content length, then what is the content accuracy, their reasoning accuracy. Okay, and we will make some final comments like for like when to use this model. So that kind of the final comments actually we will make. Okay, so let's directly start with our experiment thing. Okay, so here I already prepared these notebooks. Okay, so where I will compare the Llama 3.1 8 billion instruct inference with Llama 3.2 1 billion instruct inference and Llama 3.2 3 billion instruct inference. Okay, so first we will start with the Llama 3.1 8 billion instruct. Okay, so yeah, so this cell is regarding whatever the important libraries are there that we will first import. Okay, then in the next we will load this Llama model and create the text generation pipeline. Okay, so here you can able to see I already loaded this Llama 3.1 8 billion instruct model, and this the pipeline is there, which is the text generation pipeline, and this I am running on the CUDA on the with the torch D type bfloat 60. So I will run this. Okay, so it will take some time. Okay, so then after that if you can able to see, this is the sample prompt is there. So it is the generic example actually I am taking. So if you can able to see this is the role, means it having the two roles, one is the system role and one is the user role. So inside the system role I am saying like you are the mathematic chatbot who can explain the mathematical concept in very depth and stepwise. and I asked like explain the trigonometry. Okay, so first we will see such kind of the generic thing with a little bit whatever the mathematical terms, like how it can able to generate the output. Okay, so the same thing we will do with the Llama 3.2 1 billion and Llama 3.2 3 billion, and we will compare the output, like which it will generate the better one. Okay, so I will run this cell. Okay, then I will get the output. Okay. Okay, so it take some time to generate this output, because here I made the max new tokens 1024. So before that we will see how much memory requirement actually it is taking for the Llama 3.18 billion. Okay, yeah, sorry for the noise. Okay, so if you can able to see for the 1024 max token length, it is taking around this 15797 MB, so it is around the 16 GB. So in order to run the inference with the float 16, the minimum memory requirement it is the 16 GB. Okay, so that we will update here. Okay. That we will update here. Okay, so for the Llama 3.1 we need the minimum 16 GB memory. Okay, so let's see the output, what actually it is generated. Okay, so the now you can able to see. So I asked like what is the explain the trigonometry. So if you can see the Llama 3.18 billion output, so it is generated this content, like trigonometry is the branch of the mathematics that deals with the relationship between the sides, angles of triangles, particularly triangles with the right angle. Okay, it given I think pretty much good details. Here you can able to see the key concepts into the trigonometry, like what is the angle, what is the trigonometric function, what is the right triangle, what is the trigonometric identities. Okay, then key formulas and the theorems with respect to that. Okay, then application of the trigonometry also it is given, like where to use that trigonometry, like for the navigation, physics, engineering, computer graphics, and also it given some of the real word examples of the trigonometry. Okay, so I think it is generated pretty much good output with Llama 3.18 billion with just I can say the with the generic prompt. Okay, so now what we will do, we will see like how this output for the reasoning and programming understanding actually it can able to do. Okay, so here in order to do that, what I will do, I will take some hacker rank example, which having more complex example I will take. Okay. Okay, so let's take that. Okay, yeah, so this one of the example actually I found which is into the lace length, and it is kind of the means the complexity is the medium for this. Okay, so this example I will take. Okay, I will copy paste all this thing. Okay, so I will not make you understand like what actually this one. Okay, but what I will do, I will copy paste all this example statement. Okay, and this example statement I will give as input to the this Llama 3.1 in order to understand this logical problem. Okay, so this problem it is from the problem solving sections of the HackerRank. So there actually it is giving some logical examples, so we can able to see how the reasoning is there, how this model is understanding the content, mathematical things, and logically how it is strong. Okay, so this whole thing I will I copied. So okay, so if you can see, so this problem is based on this lexicographical order, which is also known as the alphabetical order when dealing with the strings. Okay, so this problem I will not explain you, but what we will do, whatever the output the Llama 3.18 billion instruct will be generate, that output we will paste into the this section. Okay, so I will delete this one first. Into this section we will paste, and we will check like how much this solution is correct. Okay, like we will check the correctness of this solution, like all the test cases will pass or not, we will check, and accordingly we can see like which model is best for the reasoning for the contextual learning, also the logical thing and all. Okay. Yeah, so here I already given this user content. Okay, where so first actually I created the two examples of that. So we will check the output for the reasoning and programming understanding with the generic prompt approach, where I will directly pass this user content in this particular message, and another prompt actually I created, which is more formatted one. So for the both we will see the results. Okay, so first we will see the result with this generic prompt approach. Okay, where what I did, I just copy pasted all this whatever the input means hacker rank problem statement directly here, and I just wrote here, write the Python code for the given problem statement. Okay, so now this prompt actually I created. Now we will get the output. Okay, we will see. Okay, okay, 1 minute, some issue is there. Okay, I need to kill this process. Okay, okay, so now memory is got freed, so I will just run through this. Okay, yeah, I will load the model, create the pipe, and I will directly run this our reasoning and programming understanding thing with the generic prompt approach. Okay, so now we will see the output. Okay. So let's wait for to generate Llama 3.1 8 billion instruct. Okay, so with the noise only you can see like it is processing that thing. Okay, so now if you can see, this model is generated the code. Okay, so what we will do, we will copy this code. Okay, we'll copy this code and we will paste inside the actual hacker rank content here. Okay, okay, and what we will do, we will run the code. Okay, so here you can see the sample test cases actually it is passed. So now we will see if I submit the code, so it get passed all the test cases or not. Okay, so you can able to see how much this Llama 3.18 billion, it is how much good for the programming and the reasoning thing. It can able to understand all this logical context, and accordingly it created the source also, and means all the edge test cases also we are getting pass for this kind of the difficult problem. Okay, and this we are able to do with the generic prompt only. Okay, even if I am not mentioning some specific format I created, I didn't created any specific instruction format, but still I can able to get the proper results. Okay, okay, so now the same thing we will do, like we will check. So here I created the specific format, where if you can see this is kind of the instruction I'm giving. This is the input will be there, like this is the description for the problem statement, and in the input I am specifying the problem statement, and this is kind of the formatted user content, where we are saying like below is the instruction that describe the task paired with the input that provides further context. Write the response that appropriately completes the requests, and inside the instruction I am putting the instruction, and inside the input, so whatever this context of the problem statement that I am taking there, and we will see like how this response we will get. Okay, so after this response we will get that particular response. So with this formatted prompt we will see what is the difference between that. Okay, so the same thing. Okay, I think some syntax error is there. Okay, yeah, so we'll see the output. Okay, so now if you can able to see, okay, so this source actually it is generated when I am giving the formatted instruction. Okay, and this is there, it is generating when I am giving the general instruction. Okay, so if I compare these two things, okay, so where I can able to see like means, yeah, here you can able to see it is giving the explanation also, like what is happening at the step 1, step 2, step 3, step 4, step 5. Okay, all the explanation also we can able to see. Okay, and if you can able to see the with the generic prompt, it is just generated the code, and it is like given a very small description of that. Okay, so that one finding is there, but here it is generated this thing also, like the function description, like what and all the parameters and returns thing. So this thing is missing inside this particular formatted thing. Okay, so this one difference actually I found, but the code, if you can see, it is the same one only. Okay, whatever the code it is generated, logical means the programmatically it is same only. Okay, so if I give, means we will just test like this code also it can able to pass all the test cases or not, we will check. Okay, okay, so first I will run the code. Okay, so you can able to see the sample test cases are get passed, and we will see after submitting, yeah, all the test cases are passing. Okay, so what the conclusion we can find out. Okay, so even if you having the 16 GB, means that kind of the resources if you having, and you are looking for the model which is good, like for the inference time, I can say it is taking the inference time in order to generate the 1024 tokens. It took nearly about 54.2 seconds, and in order to generate the 512 tokens, it taken the 19.2 seconds. Okay, so I can say like okay, so here I will write that thing. Okay, so for the 1024 tokens, it took around how much, 54.2 seconds. Okay, sorry. Okay, 54.2 seconds and 512 tokens, it taken around 19.3 seconds. Okay, so it is we can say it is taking more time, but the content length with respect to that, it is generating the good output. Okay, the content accuracy is also good. Okay, because I already verified this, and the reasoning accuracy. Okay, so without formatted prompts also, it is giving better means good. Okay, and with formatted prompt also it is giving good. Okay, so that we can see. Okay, so final color comments we will give after comparing these two versions also. Okay, so now let's check our second thing, which is we will check the Llama 3.2 1 billion instruct inference. Okay, so now let's move to the next experiment. So here we will see with the same the prompt, like how this Llama 3.2 1 billion instruct will generate the output. Okay, so we will start with loading these import statements. Okay, then here you can see we are loading this Llama 3.2 1 billion instruct model. So, and we are building the pipeline of the text generation. Okay, let's first we need to kill this one. Okay, yeah, I need to run again this thing. Okay, so now it can able to load this model. So the same prompt actually we are using, which is the generic prompt, where the same thing actually I copy pasted, where I'm saying you are the mathematic chatbot and who can explain the mathematic concept in very depth and stepwise, and I am asking to explain the trigonometry. Okay, so with the generic example, so let's see the output with the 1024 tokens. Let's wait. So up to that we will see how much memory actually it is taking. Okay, so this same model you can able to run on CPU also, but in this case I am running this model on the GPU. So here you can able to see it is taking just around 3 GB memory. Okay, so if you having the GPU like up to the 4 GB or even on the CPU also, you can able to run this model. So minimum requirement of the GPU for this model is the only 4 GB. Okay, yeah, so now let's see the results. Okay, so now the model generated the results. So here you can see it is generated like starting, what is this? Okay, sorry, trigonometry. It is the fantastic branch of the mathematics that deals with the relationship between angles and triangles. Then it is explained like what is the trigonometry. It explain the key concepts like angle, triangle, sine, cosine, tangent, right triangles. Then trigonometric ratios are there. Then the trigonometric identities actually it is explained. Then application of the trigonometry is there. Then the trigonometric formulas also will be there. Then trigonometric function in the real life. Okay, so like that it is pretty much means whatever the output is generated by 3.18 billion, so it is generated pretty much the same output. Okay, but we can able to see some extra content also it is generated. Okay, so for the content wise I think this model is generating very good. Okay, but we need to check the accuracy, like accuracy of the content also we need to check. So once we will generate the same output with the 3.2 3 billion thing, we will verify that also. Okay, so now let's check the reasoning thing, like the check output for the reasoning and the programming. Okay, so first I will give this generic prompt. Okay, where directly I will copy paste the same problem statement here, and I will just tell to write the Python code for the given problem statement, and I will just run this thing. Okay, so inside the system content also it is the same thing. So here I'm saying that you are coding chatbot who can give response for any programming related contest for given instruction. Okay, so then I will run this. Okay, then I will run this get output thing. Okay, yeah, so for the 1024 you can able to see how fast it is just taken the 4.3 second, and this Python code actually it is implemented So what we will do, we will just copy paste this thing directly on the hacker rank, and we will run the test cases. Okay, we can able to see it is generated some bigger content, but we need to see how much this is accurate. Okay. Okay, so I will copy paste this content here. Okay, so I will run this. Okay, so here you can able to see, so it having some syntax error. Okay, so with the generic thing only, it is not okay, it is not means with the generic prompt it is not generated whatever the output actually we need. Okay, but if you compare with the Llama 3.1 8 billion instruct, so with generic prompt only we can able to pass all the test cases. So as compared to that, I can say with the generic prompt this model is not that much good. Okay, so now what we will do, okay, so now we will see the output with the well formatted prompt approach. So as same to the Llama 3.1 8 billion instruct, I created the well formatted prompt. So the same prompt actually I copy pasted here, and in this the proper formatted prompt I given, where we can able to see this instruction input and response section with some context actually it is there. So with this we will check the output for Llama 3.2 1 billion instruct. Okay, so here I am running the inference. So here means earlier when we are running this thing with the generic prompt approach, so at that time we got the syntactical error. Now let's see the syntactical error or all the test cases are passing or not. So here I will copy paste the code there only. Okay. Okay, so here only I will copy paste that code which is generated by well formatted prompt with Llama 3.1 8 billion, and I will run. Okay, still it is having the syntactical issues. Okay, so here we can able to see the Llama 3.18 billion. It is not working well, not with the generic prompt also for the reasoning or the problematic things, as well as if I given some well formatted thing, that also it is not working properly. Okay, so that we can conclude. But with respect to the content generation and summarizing task, there actually it is working very good, because it is giving the content, the aligned content we can say it is giving. Okay, so now what we will do, the same thing we will try to do with Llama 3.1 3 billion things. So first we will kill this process for Llama 3.1 1 or Llama 3.2 1 billion thing. Okay, so kill and by 9. Okay, so I killed this. So let's try to do the same with Llama 3.2 3 billion instruct. So here I will importing the packages. Then you can see the Llama 3.2 3 billion instruct. I'm loading and building the pipeline. Okay, so first we will check the sample prompt, the generic example which where I'm saying the model to create to explain the trigonometry. The same prompt actually I copy pasted. Okay, so we can able to compare these three models output properly. Okay, so now for the 1024 tokens, we can able to see the results. Okay, so up to that, I will check how much memory it is taking in NVIDIA SMI. Okay, so it is taking around 6 GB of the memory. So at least 8 GB of the memory you need in order to run this Fluid 16 model. Okay, so yeah, so that we will update. Okay, I think it is taking too much time. Okay, so it is generated the content where it is explained this trigonometric branch of mathematics. The key concepts also it is explained, the trigonometric identities, the application of the trigonometry, the real world examples. Actually, it is given. Okay, but if I compare the length of the generated output by the Llama 3.2 3 billion with the Llama 3.2 1 billion, so that I can say it is less. Okay, so if you compare this one, so here you can able to see the more things are there, like key concepts, trigonometric ratios, trigonometric identities, applications, trigonometric formulas, trigonometric function in real life. But here that much sections are not there. Okay, so I think with respect to the content, it is not giving that much. Okay, so now we will check the output for the reasoning and the programming understanding. So first we will give the same generic prompt where I copy pasted the same problem statement here, and we will try to get the output. So here we will see the output, how it is generating. Okay. Okay, so after that, okay. So after that, I will update that table which we having. Okay. So here content length is not good. But okay, so here you can see the model generated the output. So this same thing I will copy paste there. Okay, it is generated the content. Okay, so we will try the generic prompt thing, how it is with Llama 3.2 3 billion. Okay, I will run this code. Okay, so here you can see the model. Okay, so here you can see the model generated the output without any syntactical error. So I can say with the generic prompt, it is better than Llama 3.1 1 billion, because we saw the Llama 3.1 billion, even in the generic prompt, it is giving the syntactical error, but that thing is not there. But the test cases are not passing. Okay, so for the logical point of view, still it is not that much correct. So I will check how much test cases it can able to pass. Okay, any single test case also it not able to pass. Okay, so now what we will do, with the well formatted prompt, we will check the output. Okay, so the same well formatted prompt I copy pasted here with the same problem statement. Okay, then we will wait for the output generation. Okay, yeah. Okay, yeah, so it is generated the output. So we will copy paste. So here you can see one more library, actually it is got generated, so that also we need to include, otherwise it will give error. So we will first copy this function definition. Okay, so I will paste this here. Okay, okay, then this, like this package I need to import. Okay, so now let's run this program. Okay, still it is not given that much correct, but if you can see, like only this output and this thing, only this. Okay, DHKCHCDK. No, still it is not that much correct. Okay, so let's run all the test cases, but no syntax error is there, so that is kind of, once as compared to the Llama 3.1, that is a good thing. Okay, so any test cases are not passed. Okay, so I can say, like, we means even it is not logically correct, but the syntactically it is giving the good output. Okay, without any syntactical error, it is we can able to run this thing. Okay, so here, like, we can conclude. Okay, so for the 1024 token, it is taken 9.5 second. Okay, so the content length here, it is kind of, I can say it is moderate. Okay, as compared to the Llama 3.2 1 billion instruct. Okay, so content accuracy also we will see, and the reasoning accuracy, I can say syntactically means it is kind of as compared to Llama 3 point, as compared to 1 billion, I can say it is good. Okay, because for the Llama 3.2 1 billion instruct, like for the both the cases with good with the generic prompt and with the formatted prompt, we got the syntactical error. But in this case, for the formatted prompt, we didn't got, or the generic prompt, we didn't got any syntactical error. Okay, so that is the one thing. Okay, so let's check like the content accuracy of this Llama 3.2 1 billion instruct and Llama 3.1 3 billion instruct. Okay, so for this, with the help of the chat GPT, we will compare the both the contents. Okay. 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 Okay, so here one means when discussion I already started in the chat GPT, like I said, like I will provide you the outputs generated by LLM for below prompt, and you need to compare the both and tell me the who is best. So whatever this prompt format is there, I already given. Okay, so here I will pass the output one in this way. Okay, okay, I can say the new output one. Okay, so I will copy that output which is generated by the Llama 3.2 1 billion instruct. So this trigonometric thing I will need to copy. Okay. Okay, I copied that and I will paste here, and I will tell, like I will provide the output 2 also. Provide zip to ESOL. Okay. Oh, so yeah, so he's saying like please provide new output 2. So new output 2 is generated by the Llama 3.2 3 billion. Okay, so here I need to copy this output. Okay, okay, so this new output 2 I provided, and we will check. Okay, what Okay, so the new output one, the structure is clear and consistent. It introduces a topic. The new output also well structured, covering the similar concept. However, it spend more time on advanced trigonometric identities. Okay, so best for beginner audience, like the new output one is good, but for the depth explanation, the focus on the explaining the basic trigonometric function while it introduces more advanced concept and identities. Okay, so yeah. So for the mathematical details, new output one focuses more on the introducing the basic entities and provides some more comprehensive list of identities. So if the goal is to provide the beginner-friendly explanation with clear and potential in the context, new output one would likely be better choice for a general audience looking to understand the basis of trigonometry. Okay, so here I can say like means so whatever the output which is generated by the Llama 3.2 means if the use case which is very where you need very the depth details, okay, depth analysis and all that thing. So at that time you can consider this Llama 3.2 3 billion. Okay, but something simple things are there and the resource requirements also are less. So at that time you can consider this. Okay, so here the I can say the high level details it will give, okay, for the content accuracy, and here we can able to see the depth level details. Okay, so I can say in the final comments like Llama 3.1 8 billion instruct, it is I think the GPU memory is large, which is 16 GB, and the inference time is also large, but the content length is good, content accuracy is good. Okay, and without formatted prompt, with formatted prompt is generating the code output. Okay, so but as compared to the Llama 3.2 with Llama 1 billion with the 3 billion, so it is taking 4 GB of GPU memory, and this one it is taking, it required the 8 GB of taking it's required 8 GB GPU, but from that it is actually taking 6.5 GB something. Okay, and it is taking the 4 second for the 1024 token, it is taking 9.5 second. So the content length I can say the Llama 3.2 1 billion, it is the good content length is there. But as compared to the Llama 3.313b, it is the moderate. Okay, and the content accuracy, the Llama 3.2, that much depth details you're not able to see. High level details are there, and inside the Llama 3.1 3b Instruct there are the depth level details are there as compared to the high means 1 billion. Okay, and the reasoning accuracy, it is not good for the 1 billion. Okay, but as compared to the 1 billion, this for the this 3 billion model, it is giving the good means it is kind of good because it is not generating any syntactical errors. Okay, so this kind of the final comments I can give here. Okay. Okay, so yeah, so this is for the today's session, so where I explained all the details about the Llama 3.1. Okay, then like how they compress this model from the 8 billion to the 1 billion, so that details also I given. And also we gone through this pruning and distillation mechanism into the depth. We saw the things like how it is working. Then we did this practical thing, like where we compared the model outputs of the Llama 3.18 billion Instruct, Llama 3.2 1 billion Instruct, and Llama 3.1 3 billion Instruct. Okay, so I think the most of topics are I covered. Okay, so there is the how to fine tune this model. So that also I will make one video for that. But for now, that is these are the things are there. So if you still not subscribe my channel, please subscribe and yeah.
Thank you so much.